Okay, very well. Yeah. So definitely this, let's
Professor,
say,
Professor,
can you hear me?
yeah,
Yes.
I can hear you. Can we start the proceedings from here?
Yeah, sure, not a problem. Yeah.
Over to you, Dibu sir.
Yes. Thank you, Praveen,
Okay.
sir.
Okay, yeah. So first of all, thanks for inviting me here. Yeah. So I would be happier if this is a real in-person meeting. Yeah, but I understand that people are very busy nowadays. Yeah. All right. So the idea
Sir,
was to,
shall I just introduce you? I mean, before the presentation, I just need to introduce you to the participants. Shall I do it, sir?
Professor, Dr. Dibu is waiting to introduce your profile so that we can start the talk.
Okay. Well, good.
Good afternoon, everyone. Hari Om. A warm welcome to the International Conference on Recent Advances in Composite Materials 2024, ICRACM 24, organized by Chinmaya Vishwavidyapeeth deemed to be university. We are delighted to have such an enthusiastic and diverse crowd to participate in this event. Before we begin, I would like to tell you a few things. Please keep your mic muted, and we hope that you will very actively listen and take notes so that you can ask questions at the end. And at the end of the presentation, you can ask questions in the chat, through the chat. Now, it is my privilege to welcome our esteemed keynote speaker, Professor Miran Mozetic, a luminary in the field of material science and engineering. Miran Mozetic received the Diploma Engineer degree in physics from the University of Ljubljana in Slovenia in 1988 and a PhD degree in electronic vacuum technologies from the University of Maribor in 1997. He served as an engineer at the Institute of Vacuum Technology and Electronics, Ljubljana, between 1988 and 1995, and as a head of the plasma laboratory at the Institute of Surface Engineering and Optoelectronics, Ljubljana, between 1995 and 2003. Since then, he has been with Jozef Stefan Institute, the largest research institute in Slovenia. He has been serving as the head of the research unit since 2009, currently involving about 30 researchers and technicians. He has co-authored 400 scientific papers and was granted 30 patents in the niche of plasma technology. His H-index is 60, and his current interest is the application of extremely non-equilibrium states of reactive gases for tailoring surface properties of solid materials. Today, Professor Mozetic will share his insights on adjustment of surface properties of polymer composites by treatment with gaseous plasma, a topic that underscores his dedication to advancing material science. Please join me in giving a warm welcome to Professor Miran Mozetic. Over to you, sir.
Well, thank you very much for this kind introduction. Well, actually, I have two affiliations. One of them is with the Jozef Stefan Institute. The other one is my spin-off company, which is Plasmadis. So about 10 years ago, we established a spin-off company to trade our innovative solutions. All right, so today I will speak a bit about surface properties of composite materials. Well, everybody knows that any material interacts with the environment through its surface. So it's very important what sort of surface properties we have. The best way of modifying surface properties is treatment with gaseous plasma, and we can either use atmospheric pressure plasma, which is on the right-hand photo here, or low pressure plasma. Well, everybody can see that with the naked eye that atmospheric pressure plasma, we never get uniform plasmas, and we never get uniform treatments, whereas low pressure plasmas enable uniform treatments. Okay, so let's continue with the next slide. All right, so polymer composites are widely used. Okay, next slide, please. Now, this is just schematic of any polymer composite. So we have fillers which are embedded in a polymer matrix. And all these fillers are, because of the production process, they're actually covered with the polymer, so they don't stretch outside. So it means that the surface properties of these composite materials do not depend on the type of fillers, but rather only on the type of polymer. And by far the most important surface property is wettability. Next slide, please. All right, so here we have two examples, two extremes. Yeah, one of them is hydrophilic surface finish, the other one is hydrophobic. This hydrophilic surface finish is caused by highly polar surface functional groups and also rather rough surfaces. I'm talking about roughness on nanoscale or sub-micrometer scale, okay? On the other hand, we have these highly hydrophobic surfaces, and this surface finish is obtained by non-polar surface functional groups. Next slide, please. These are examples of polar and non-polar groups. I don't want to go to too many details. I only want to say that those groups which are polar, they are those groups which contain oxygen, actually, these are polar. So polyolefins are not polar, but polymers with this carboxylic group or amide group, they're highly polar. So next slide, please. It's interesting that none of the known polymers is extremely hydrophilic, so it means that the water contact angle will be very low. Yeah, so we have to use different techniques for increasing the hydrophilicity if this is our goal, and this is our goal if we want to coat the polymer composites with a functional coating. So historically, people were using this wet chemistry, but this is rather dirty technology. So nowadays, we all use gaseous plasma treatment. So this photo here shows a gaseous plasma in, I think it's about 20 centimeter diameter of the discharge tube, and there's some kind of a transport belt which runs through plasma at the speed of 1 meter per second. So next slide, please. When we are talking about plasmas, non-equilibrium plasmas, the basic property of such state of the gas is that the gas temperature is very close to room temperature, but the temperature of free electrons is very high, so it's several 10,000 degrees Celsius. So these are very energetic electrons, and such electrons are capable of ionizing, exciting, and dissociating molecules. So in the case of oxygen plasma, normal oxygen molecules are just O2, but in plasma we get different highly reactive species like positively charged ions, metastables, and neutral atoms. And one very important thing which is usually overlooked, if you read the literature, you cannot read much about this. I'm talking about energetic photons. So this spectrum below in this screen, this is a spectrum of typical oxygen plasma. So in the visible part of the spectrum, there's not much. It's only something at 777 nanometers, so it's in the red part of the spectrum. So that's why oxygen plasma glows red. But we can see here at the wavelength of between 100 and 150 nanometers, we have very strong radiation. So the energy of these photons is about 10 electron volts, and that is higher than any chemical bond in the solid material. So it means that when you treat whatever material with oxygen plasma, it means that you will break bonds in the surface film because of these photons, and you will also cause some kind of surface oxidation because of this reactive species. Next slide, please. Okay, so when you expose any organic material to such oxygen plasma, you get spontaneous formation of these functional groups. We have different functional groups. As the result of the creation of such functional groups on the surface is that the hydrophilicity is improved dramatically. Next slide, please. If we really want to understand what goes on the surfaces of any material, we have to make a good theory. So the theoreticians can explain extremely well what goes on the surface. There was actually no useful theory about surface activation of polymers with oxygen plasma until 2020, yeah, so 4 years ago, yeah, when this group from Tokyo Electron from America, yeah, they published an excellent paper about the theory of oxygen interaction, oxygen plasma interaction with polymer surfaces. I don't want to explain much. Yeah, I only want to stress that there are numerous binding sites for oxygen atoms on the surface, but the site with by far the highest absolute value of the adsorption energy is for the formation of hydroxyl groups on the surface. So the theory says that if you expose your polyolefin or any other polymer to oxygen plasma, the first reaction that will occur will be formation of hydroxyl groups on the ring atoms. And then they calculated that the next effect should be degradation of the aromatic ring. So opening this chains, and then the formation of other functional groups. So this is the theory, and this is from a group from America. And please, next slide. This is experiment. That's our work. So we found, we precisely dosed the oxygen atoms, which are main reactants in oxygen plasma, and you wouldn't believe that the experimental results are practically identical as the theory. So by far the most probable reaction is formation of surface hydroxyl groups, which occurs already at a very low dose of oxygen atoms. We're talking about less than 10 to the 20 per square meter. So at least those low doses, nothing else happens. But then we can see at the dose of about a few times 10 to the 20, this green dots becomes lower, and they indicate the degradation of the ring. So it's exactly the same as the theory says. And only after the ring degradation, we can create other functional groups on the surface. So I'm talking about black dots, yellow dots, and blue dots on this spectrum. So the theory and the experiment in this case are very, very sound. So we can conclude that we know practically everything about surface functionalization of polystyrene in this case, but also similar results for other polymers. So next slide, please. Knowing everything about the surface functionalization is very nice, but we have to focus on the wettability. The wettability depends on many things, and if you read the literature, you will find out that practically all authors show the wettability as a function of the treatment time. So we performed experiments in our plasma reactor, which is rather flexible, so we can change the plasma parameters in the same reactor. And what we see here on the left-hand side diagram is the evolution of the surface wettability versus the treatment time. What we can see is that we can get practically any result. So at the treatment time of 1 second, we can see that either we get practically no modifications in the wettability, or we get almost super hydrophilic surface finish. So the treatment time is not the parameter which tells you anything about the surface wettability. What is parameter is the the dose of neutral oxygen atoms. So I said before, that the main reactants are neutral oxygen atoms in oxygen plasma. And this diagram in the right-hand side, it contains exactly the same measured points as the other diagram on the left-hand side. But in the left-hand side, it is versus the treatment time. On the right-hand side, it is versus the O atom fluence, or it means O atom dose. So this is very persuading confirmation that the surface finish depends on the dose of atoms and not the treatment time or the size of the reaction chamber or the discharge power or anything else which is usually reported in the literature. Okay, let's go on. Another, okay. So I said before, that theory and experiment tell you that the first reaction on the surface of polymers should be substitution of CH bond with the hydroxyl group. But what about Teflon? I mean, Teflon doesn't have any hydrogen in the structure. If you treat Teflon with oxygen plasma, you will get any surface finish. So this diagram here, it's water contact angle versus the concentration of oxygen in plasma. It shows that there's no correlation actually. So you can get any surface finish independently from the concentration of oxygen. So how can we explain this paradox? Very simply, the binding energy between carbon atoms is lower than between carbon and fluorine atoms. So it means that the net effect of treatment with oxygen plasma is just etching of Teflon and not surface functionalization. So next slide, please. If you want to make Teflon super hydrophilic, then you have to use a different technology, so not treatment with oxygen plasma. Although in some literature you can read that it works. I tell you it doesn't work, but I recommend a two-stage treatment. So first one is the treatment with hydrogen plasma, and the next one is treatment with oxygen atoms. So hydrogen plasma is a fantastic source of vacuum ultraviolet radiation, means radiation with the photon energy 10 electron volt or more. So this radiation just breaks bonds between carbon and fluorine. And the dangling bond is just occupied with hydrogen atom. So what you create by a brief treatment with hydrogen plasma, talking about 1 second or less, you create some kind of polyolefin-like surface film, which is very thin, a few nanometers only. But that's enough, to use oxygen atoms then to create these highly polar functional groups. So this diagram here, it shows the evolution of surface wettability versus the dose of oxygen atoms. So we are always doing versus the dose. And well, we can see there's a very beautiful minimum in the curve at the dose of about 1 × 10⁻23. And this minimum is at the water contact angle of below 10 degrees. So Teflon can be made super hydrophilic using this technology. Teflon is just the worst case. So using this technology, you can make any polymer super hydrophilic. By the way, we got American and European patent on this. Okay, so next slide, please. Well, the surface is sooner or later saturated with functional groups. And if you prolong treat this polymer with oxygen plasma, you stimulate something which is called low temperature burning. So it's just etching, okay, etching with oxygen radicals, and this etching occurs at room temperature. This etching is, I think, never laterally homogeneous, but it is heterogeneous, means that you create spontaneously some kind of nanostructures on the surface. So next slide, please. This one, yes. No, this one, yeah, this one. So this is AFM image on the area 1 × 1 micrometer of originally perfectly smooth foil, polymeric foil, which was treated with oxygen atoms, and we can see this beautiful nanostructured surface, which in combination with polar functional groups assures this super hydrophilic surface finish. So this roughness and activation with polar groups always causes super hydrophilic surface finish. Next slide, please. Okay, so I said that the surface properties of composites depend on the surface properties of polymers, and I explained how to modify the surface properties of polymers. In some cases, however, we don't really want to have really polymer on the surface. We want fillers on the surface. And well, it should be a movie to show how we remove these fillers, but it doesn't work in PDF. So please, next slide. Yeah, after treating our composites with oxygen plasma, we cause selective removal of the surface of the polymer film. So this scanning electron microscope image in the left top part of the screen, yeah, this is a typical image of untreated composite. So we can see that there should be some kind of particles inside, yeah, but they're covered with polymer. Now, after treating with oxygen plasma, we remove the polymer. So on the surface, we can see these fillers. So in this case, the surface properties don't depend on the polymer anymore, but actually on the fillers. And that's very important in the case where, for example, we want to use different conductivity of materials, because we know that with polymers we're limited. Originally, we developed this technology for paint industry, and at present we have several companies, not numerous, okay, about 10 of them, who are using this technology to reveal the distribution and orientation of fillers inside their paints. So this right-hand image, it was taken after the plasma treatment, and we can clearly see that there are numerous flakes and some other particles which are nicely oriented, so it means that this paint is good. So if you want to do some kind of reverse engineering, you are interested in what sort of fillers and what sort of distribution of fillers is in the matrix, in the polymer matrix. You just use oxygen plasma and you will uncover the secret. Well, in this case, I must say that the required dose of oxygen atoms is larger than in the case of activation of polymers, just because you have to ensure etching. Etching takes time. So the recommended dose of oxygen atoms is about 10 to the 25 atoms per square meter. Next slide, please. Okay, let's show one application of this selective etching. These are commutators. Next slide, please. All right, so this in the middle, this is untreated composite material. It's graphite grains embedded in the polymer matrix. And on the right-hand side photo, this is a photo of the final product. So this graphite polymer composites, it's raw material. It should be somehow connected to this copper electrodes, and you may know that connecting polymer with metal, it's not a trivial task because of the differences in the surface energies. And furthermore, these products, they should withstand thermal and mechanical loads. So next slide, please. All right, so this is just schematic. So on the left-hand side, we have this schematic of the composite material. This composite material should be covered with something gray here. So it's a layer of metal. There is a classical technology for metallization of, I think, all known polymers. And the classical technologies include different steps. The most expensive is electrodeless nickel, and the most dirty is palladium sealing, because it's a cyanide solution. So this combination of 5 different technologies, this will ensure good metallization. However, this technology is, first of all, dirty. So lots of waste chemicals. Sorry? So first of all, it's dirty, and then it's also expensive. So we changed this technology. Next slide, please. Next slide. And we developed this production line. So this small pieces inside, it's what you saw before. What we saw before. So it's a system with a capacity about 1,000 pieces in a batch. And it's only oxygen plasma inside, and the treatment time is not long. So we're talking about half a minute for the etching, and using this plasma system, we have a big production of these components. Next slide, please. So what plasma is doing with our composite material is that it selectively removes the surface polymer film. So on the right-hand side, we see evolution of the roughness. So originally the material is smooth, because it's polymer on the surface. But then after appropriate treatment, it's very rough. And well, unfortunately, we cannot see evolution of wettability because it's in the middle diagram, but you can see that at large doses on the right-hand side, we get 0 water contact angle, so super hydrophilic surface finish. So it means that by treatment with oxygen plasma, we reveal the graphite grains of the surface and we make them super hydrophilic. And such a surface finish is useful for direct galvanic metallization. So next slide, please. So with our plasma treatment, we managed to replace 4 different technologies. So I showed before in the photo of this reactor, plasma treatment is simple. So once you know the technology, it's very reliable, and it's also much cheaper than this chemical treatments. So with this oxygen plasma treatment, we can create such a surface finish which allows direct galvanic metallization. So this technology is much cheaper, and also it doesn't produce any waste. So next slide, please. And next slide, please. All right, so at present, I think we still have 70% of the world market share in this segment. So it's these commentators here, because our production is just much cheaper than what the competition is doing. And also it's very well protected with different patents, but I cannot see Indian patent here. So in India, you can use freely this technology. Okay, next slide, please. Yeah, I hurried up, yeah, because I spent quite a lot of time with my computer problems. Yeah, so I think I have 2 minutes left. Yeah, that's enough time to thank to you, of course. Yeah, and to thank to the partner or my co-workers, yeah, who are also the partners in my spin-off company. So this gentleman, Prof. G. Primt, he's my previous PhD student. Now he's the director of this company. So once we know this doses, fluencies, whatever, then we can go really upscaling the technologies. I didn't show because I didn't have time. Yeah, we developed numerous large plasma systems. This one, what we show here in this photo here, this one is actually 16 meters long, so 16 meters. And this is obviously it's used for treatment of materials in the continuous mode. Yeah. So if you know this scientific background of the technology, and then upscaling is only a technological problem and not a scientific problem anymore. So thank you very much for your attention.
Thank you so much, Professor Mozetic, for such an insightful and thought-provoking keynote on adjustment of surface properties of polymer composites by treatment with gaseous plasma. Your expertise and innovative perspectives have truly enriched our understanding of this critical area in material sciences. Now we would like to open the floor for questions. I kindly request the audience to type their questions in the chat box so we can address them one by one. Any of the participants, if you have any questions, please can ask in the chat.
Yeah, well, that was a specific topic, and I must say that the time is running out. Yeah, so I'm very sorry about these complications with the computer. But if somebody is very much interested, please just send me an email.
Yeah, sir, there is one question. It's about the stability of plasma with time.
Yeah, this is a very good question. Yeah. All right. So it's a nightmare for technologists. Yeah. Of course, the concentration of radicals in plasma depends on many parameters, and usually it drifts with time. So the question is very good. Yeah, we always observe some kind of drifting. So our industrial systems are equipped with the probes for measuring the concentration of major reactants. Usually it's only oxygen atoms. These are most important. And if the concentration goes beyond the recommended values, then automatically we change something. So if the concentration becomes too small, then we increase the power automatically. Otherwise, we decrease the power. Yeah. So having plasma with constant parameters, it's practically impossible.
Thank you, Professor. Once again, thank you so much, Professor Mozetic, for joining us today. Thank you, everyone, for attending the session. Have a good day. Next, we will have a technical session. Over to you, Dr. Praveen.
And thank you, Dr. Deepu. And Professor Miran, thank you. Thank you for the nice talk, and hope we can meet soon.